for today, we're going to continue what we did in last lecture. In the end of lecture 2, we discussed the phase change of water. We said, for example, if you remember, we have, for example, the PV diagram or TV diagram, temperature specific volume diagram for water. It look like this. We have two important lines. We have three regions. We said we have three regions, two lines, and 1 point. And they are like this. We have subcooled compressed liquid here, compressed liquid, subcooled. We have saturated mixture. We have superheated vapor. Superheated vapor. So if you follow the constant pressure line, let's say I give you 1 atmosphere, constant 1 atmosphere, and you follow this line, you'll find something like this. This is 1 atmosphere. No matter what, if you have water liquid at 1 atmosphere, your specific volume is about to be 0.001 meter cube per kilogram. It's going to remain in this range. Then, at certain temperature, which is exactly 100 Celsius, the water starts to evaporate. Yes, here the vapor started. Almost no vapor, zero vapor. This is called saturated liquid line. And it starts to evaporate until it became complete vapor here. We call it saturated vapor. This is 2 lines. Then it can be completely vapor. Temperature will increase. This is specific volume, temperature cap. This is a constant pressure line. Constant pressure line means temperature and specific volume proportional to each other. So the pressure, there is no pressure. Pressure is constant. So this and this increasing this volume approximately increases the temperature. Here, the specific volume is 1.67 meter cube per kilogram. A very famous 2 numbers. This is exactly 1 liter, like this. Remember this forever, 0.001. And we said we have here this point. It's called critical point. The critical point has a specific volume. I remember it's 0.03. It has pressure critical of 22 point, I don't think megapascal. It means 220 atmosphere, almost 220 atmosphere, 3.5, something like that. And temperature critical, I remember 374 point something Celsius. This is the critical point here, this point, green line. So what happened? If you keep increasing the pressure line, this one like this one like that, 2 atmosphere, 3 atmosphere, 100 atmosphere, 225 atmosphere, everything changes dramatically. Like it was liquid, suddenly became vapor. So at one point, everything it changed from complete liquid to complete here in a region from here, from 0.001 until 1.67. So the volume keep increasing from 1 liter to almost 2 meter cube, 1.67 meter cube. It takes increase in the volume. Here, at this specific volume, at this pressure, the water changed suddenly from liquid to vapor across this critical point. Now, what we can do with this? Why we are doing that? Are we just giving you something for no reason? No, this is important. All the steam engines, all the power plant working based on this concept. You need to know how the water behaves to study a problem. I will show you right now today a lot of problems, simple problems. Next lecture, a little bit harder. The following next lecture, and so on. Every time we're going to add some complexity to the problem. But this is very simple. If your temperature, for example, if I told you you have 1 atmosphere and your temperature is 40, so you are sure you are here. It means you are subcooled. If temperature is 100, it means you are mixture either from here or here or here or here or here or here or here, anywhere between these 2 points. From complete liquid to complete vapor. And this line, if you have temperature 101, 100.1, 200, 300, it means you are superheated vapor, like my coffee. Okay? Now there is not. But my wife now they recognize that this is killing me. So, superheated vapor. We give the same plot for PV diagram. PV diagram. We plot everything, but between pressure and specific volume. We have exactly the same curves, the same data, the same everything. But we plot the constant temperature line. It was like this. I'll describe why. This is constant. Let's say temperature is 100 Celsius. Okay. Now this is the confusion. When I plot these guys, PV diagram at constant temperature line, do not think about temperature. Do not think about temperature. Ever.
What happened in this PV diagram along constant temperature line? Along constant temperature line. Forget about temperature. We're now seeing P versus V. For example, let's take an example. If you remember from equation of state, ideal gas law, P equal rho RT, or maybe, but instead of rho, we can say the RT over a specific volume, because specific volume is 1 over rho, correct? So if the R is constant and temperature is constant, along this line, always temperature 100 Celsius, 373.15 Kelvin. The pressure and the volume, specific volume, are inverse proportional, especially in the gas region. This is a superheated, this is a gas. So decreasing the pressure, increasing the volume. If you have a tank.
Excuse me, Professor?
What?
Excuse me, the stream looks worse, like it's still really blurry.
What? Okay, next lecture I will make it in the school because it look like it's not here in the house. Okay, next lecture I'll make it at school. Okay? Can you hear me, guys?
Yes.
Great. So sorry for today. This is the last day when we get home. And next time I'm gonna make it in the school. The internet much faster there, especially the wire. So for now, just be patient. I already uploaded the lecture. It's written, but today just try to follow me as much as you can. We're gonna make video also for this in the learning class. So the pressure and specific volume are inversely proportional to each other. Increasing the volume, decreasing pressure, or increasing the pressure, decreasing specific volume, and vice versa. So here the volume increases, the pressure drops, especially in the gas region, because this equation sometimes valid in the gas. Here, superheated, which is gas. Okay, so generally it decreases like this. The pressure, volume relationship like this, decreasing, while the temperature is constant. So do not confuse with temperature at all. When I plot this line, forget about temperature. Temperature is constant. When I plot this line, forget about pressure. The pressure is constant. The temperature with volume. Increasing the temperature increases the volume. Increasing the specific volume, increasing the temperature, as long as the pressure is constant. Now, if I give you this temperature Compressed liquid. If I give this temperature, superheated vapor. If I give you this temperature, you are mixture, either here or here. So you have compressed liquid, solid mixture, solid vapor. So what happened in this today's lecture? We're gonna go dive in more details about this data. And actually we can plot also the PT diagram. Okay, this is section 3.4, was 3.4. Okay, guys, following me? Say yes or no, please.
Yes.
Great. So we have three options, guys, here. We have three options for data. Three options for any data in the world. For any data, we can have either table between, let's say, X and Y. I give you X, I give you Y, if they are dependent. I can give you chart, a figure, let's say X and Y. I give you X, you get Y. So you can give table, a chart, or maybe equation, like curve fitting or whatever. Y is a function of X. Put X, get Y. So I have three ways to see data: through table, chart, and equation. It depends how the data big. Here we have a huge data. We have significant number of inputs. So in 3.5, we're gonna talk about property table. Property table. That is, we can collect the water or any fluid data in a table, and we call it property table. Actually, we're gonna use this or this or this, but now we're gonna focus on table. For example, we have in your book tables A4 to A11 just for water. We have table, I think I don't remember, 12 or more to A14 for R134. For every gas or every fluid, liquid, gas, or even sometimes solid, but for now we are talking about liquid and vapor of this liquid. Let's say water. If you're talking about water, what is this? If you're talking about water, it's from A4 to A11. A4 has something, A5 has something, A6 has something, A7, A8, until A11. They are all for water. If you open, I also uploaded for you the same table in the reference book. A12 to A14 is another fluid. Every table, guys, has some data, So let's talk about the water now. For example, A4 and A5. Actually, A4 the same as A5. I'm gonna remove this. Now we are 3.5. We're talking about the steam table. The steam table. A4, for example, A4. Can every one of you open now A4 for me, please? A4, it has pressure, temperature. You have VF, VG, maybe VFG. You have HF, HG. Let me make it bigger to see a lot of information. P, or actually T first. P, VF, VG or VFG, HF or UF first, UG, UFG, HF, HG, HFG. Can any one of you open this? Please, table A4. It's in the files. If you go to the files in your computer, you will see the table steam tables given for you from A1, A2, A3. If someone find it, say yes, please.
Yes.
So the steam tables are given for you, as I said. Go below, go down until please section. I can share it with you, no problem. Let me share it with you. Would be better for everybody. Let me download it here. 1 second. Open it. Then I will share it. Let me share it with you. Okay, can you see now? So now I'm sharing the steam table, which is starting from here. Saturated vapor, for example, for water, A4. Let's go down to A4. A3, A3, A4. Here. This is A4. Can you see? It started at almost 0 Celsius, like 0.001 Celsius. This is the pressure, saturated pressure, saturated volume, liquid volume, liquid vapor, U, H, and finally S. Let's, for example, look at 100. Can you see the 100 line? This one. Can you see this line, guys? It's called 100 Celsius. This line has temperature of 100. It means this line is 100 Celsius. The pressure, saturated pressure, is 101.32. This is in Celsius. This is in kilopascal. This is meter cube per kilogram. The same meter cube per kilogram. This is not there, but we can put it. This is kilojoule per kilogram. Kilojoule per kilogram. Kilojoule per kilogram. Kilojoule per kilogram, and so on. So what's happening here? Can you see this line, guys? The 100 Celsius? Yes? No?
Yes, we can.
Yes.
Yeah. So somebody can give me the VG. The VG at this line. VG.
1.620.
72. 1.67220. How about the VF?
0.001043.
43, correct? Yeah, 43. Great. Okay. If you remember, these are the 2 points we were talking about. This is 1 liter, and this is the almost 2 meter cubes per kilogram. So if I give you 1 kilogram of water, I told you this is the temperature, this is the pressure, of course, in between those. This is, we call it F, which is mean saturated liquid. Whenever you see the F subscription like this, it means subscript, it means saturated liquid. G like this, it means saturated vapor. Saturated vapor. The same for internal energy. This is called internal energy. We talked about it before. Actually, this is not internal energy. Can someone correct me? What is this exactly? Small, not uppercase, lowercase. So it's what? Lower case U is what? Not upper. It's specific. Perfect. Specific. It means we divide by mass. Kilojoule per kilogram. The whole column. It means intensive property. It's not depend on the size. No matter what you have, how much water. Of course, if you have 100 Celsius, 100 kilo, 1 kilo, 0.1 gram, you have the same data. VF, UF is this, a specific internal energy. This is called a specific enthalpy. We're gonna talk about it right now. Enthalpy. I'm gonna talk about it right now. So again, we have VF. NF means liquid. Energy means vapor. Remember this forever. Somebody is coming to laugh and hello. Okay, you can make it mute and laugh as you wish. Okay, guys. I don't know. Did I say joke? So here we have F is liquid, G verb vapor. Okay, and always this is 1 liter. This is, you will see this always at 100 Celsius. If you have pure water at 1 atmosphere, you always see this line, or 100 Celsius. I mean, no matter where you see this G, it means saturated vapor. F, saturated liquid. This is called internal energy. No, specific internal energy. The total, the summation of all internal energy within a system, not potential energy, not kinetic energy. It's actually molecular and nuclear energies. This one, internal energies. What is enthalpy is? Enthalpy is like this.
Professor, I realize all we can see is table A4, right?
Yeah, table A4. This is table A4. Can you see it, guys? Table A4 in page 904.
Never mind, yeah, that's all we can see. We can't see what you're writing on the board, though.
You cannot see my board? Oh. Yeah, wait. Let me
Yeah,
stop.
you can.
I'm gonna stop sharing. Now you can see it. Can you see?
Yeah, we can see it now.
No. Okay, so temperature. I'm now getting data from after you saw table A4. Forget about table A4 now. We took some line. We see temperature input, pressure also input, saturated temperature corresponding to this temperature, a specific volume at the liquid line, specific volume at vapor line. The difference, if it's not, we're gonna get the difference. I think it's not there. VF, UF, UG, UFG, HF, HG, HFG. Okay. So this is U, small u, is specific internal energy. Specific internal energy because we divide by mass. No matter you have 100 kilo, 1 kilo, 0.1 gram, this is a constant value per fluid because it's per kilogram. No matter what you have, it's specific, it's intensive property. A specific enthalpy. Enthalpy is like this. It's still with 3.5. Enthalpy is a very important parameter. It's energy. We use letter H. Sometimes you call it total enthalpy. Total enthalpy. It's H equal U plus PV. The total enthalpy is total internal energy or internal energy plus PV. Pressure, which is Pascal times volume, it's a work. This is called work or flow work. We call it flow work. This total term, internal energy plus flow work, PV, the product this, is called enthalpy. We have seen it a lot. You're gonna when I talk about open system, you'll see this one a lot. That's why we get a new property. It's called H. Enthalpy. If I want a specific enthalpy, a specific enthalpy. What is big enthalpy? It's H small. It's equal U small plus PV small. So we divide by mass, became a specific enthalpy. Divide by mass, a specific internal energy. Divide by mass, it became a specific volume. Pressure times specific volume. For example, if you go to this value, HF, at this 100 Celsius, if you want to get this value, it is exactly UF plus P times V. So if you want HF, it's UF plus P VF. If you want, for example, if, you're gonna get exactly the same value. So this column, actually, we don't need it, but it simplifies the calculation. Sometimes you will see this term a lot of time. Instead of getting P multiplied by V, then add it to U, we add new data to simplify the calculation. So this guy, we call it H, enthalpy, or specific enthalpy here, to be independent of the size of the system. It's intensive property. Any question? A steam table, you need carefully read the steam table, like read the problem and read the data. For example, we're going to take some examples, 2 examples. If you have a steam table, guys, like this, you have, okay, if you have a steam table like this, and you have the constant pressure line like this, as I said before, if I give you the temperature at this pressure, for example, you can get a specific volume. If I give the temperature, you can get the specific volume. Let's take some problems to solve this. Some problems to show how we can do this. I'm gonna start here. I'm saying at 90 Celsius, determine, please, VF and VG. Can somebody tell me what is VF and VG at 90 Celsius? And 90 Celsius, guys. What table? What table?
VF is 0.001036, and VG is 2.3593.
Perfect. Meter cube, of course, per kilogram. I want always you to write the unit next to the variable. Here, guys, I want you to learn 2 things. Even without looking at the table, you're expecting to see 001. 001. This is temperature, and I'm asking about the liquid. At almost 100 Celsius or a little bit lower, you will see 001, then some numbers. So you expected to see 001. Also for VG, you expected to see, remember 1.67? No, a little bit larger because temperature is lower. So actually here, you have a little bit lower temperature like this. So you have this guy and this guy. The volume VG a little bit larger, VF a little bit lower than the 900 Celsius. How about if I give you, for example, how about if I told you, please add, let's say, 200 kilopascal. Determine VF and VG. Of course, you will find out table A4 is not good. You need to go now to table A5 because temperature here is input. So the better is to go to table A5. Please go to table A5. You will see it's exactly the same as A4, but the input, the very, very left column is pressure. Go to please the table A5. You will see you going steps in pressure. Much better than having table A4, which is inputs in temperature. Yeah, table A4 is very good if temperature is given. A5 is perfect if pressure is given. I mean, in terms of steps. Can you see table A5? Can you see, guys? Can give me a VF and VG saturated a specific volume at saturated pressure of 200 kilopascal?
VF is 0.001061.
VG
0.8088
as you can see,
578.
it's okay. So 0.08 or 0.8, I don't remember, I do not hear it well. Anyway, the point is like this. When you add more pressure, now if you plot it, like even this curve, it doesn't matter much, this one. This is like, for example, 200 kilopascal, which is about 2 atmosphere. You will see here, the volume here a little bit larger, and the volume here a little bit smaller. But still, we still can see the 0.001. Oh, sorry. And here, around 1 meter cube per kilogram. So we still 0.0, about 1. So you still see the same value. I want you to feel these numbers. Here, we see always 0.001 something, and here around 1 meter cube per kilogram, 2.8. Here, exactly 0.033. This is the critical point. So you can feel this table. If you have volume with 0.001, it means you are very close to compressed liquid. Around 1, like 2 point something, 0.8, you are still more in the vapor side. If you 0.03 or I think 00, it's critical point. 0033 is the critical point. In between, at lower pressure, temperature, in between saturated mixture. Okay, so now we can easily get a simple value if I give you temperature or pressure. Guys, at this pressure, there is something very important called T saturation at 200 kilopascal. What is the temperature, guys? The second column. Can you give it to me? In this row, the second column is called T saturation. Is what? Table A5. You need to follow me, please. Open table A5. Look at, for example, 200 kilopascal, and give me the T Celsius at this pressure. What is this?
120.21.
120.21?
Yes.
So this is the boiling temperature at almost 2 atmosphere. So if you have a pan, you want to cook something, and you keep the pressure inside constant, 200 kilopascal. This is the temperature at which the vapor will start to evaporate. Below this, if you have 100, 110, it's not gonna. You never ever see vapor. If you keep the pressure constant, and pure water. If you keep pure water, pressure 200, you will never ever see vapor below this. So also you need to feel the steam table. If you have this line, 200 atmosphere, if you are here, you're impossible to see vapor. As long as you lower 120.21 Celsius, it's impossible. But once your temperature go to this value, vapor start to show up. You go from here, along this line, at constant pressure line, till here. So you go from this volume to this volume. If you keep going in constant pressure line, you can go this way. The volume keep increasing with temperature. And the pressure is constant. Pressure is 200 kilopascal. So the table A4 and table A5, exactly these lines. This is, we call it V, or anything, subscription with what? F, subscript F. And here, anything with subscript G. 2 saturation lines. Okay, guys? So far, so good?
Yeah.
Let's take some examples, a lot of examples. So let's take a lot of examples now. To every one of you, please, paper and pen, simple calculator, and the steam table, open it. And I'm gonna give you like 6, 7 problems. For every one of these, please find the data yourself. This is exercise for you. And when after the lecture, you can do more examples. All these examples already given in the lecture 3. I already posted lecture 3, 4, and 5 to the end of the week. So if you want to read, solve as you wish. A temperature of 120 and a pressure of 150. Give me what is this? Is it compressed liquid or mixture or superheated vapor? Tell me why. What is this and why? Letter B, problem B, its temperature 65 Celsius, pressure 25.03 kilopascal. What is this again also? C, 200 kilopascal. Actually, we did this already. 200 kilopascal. And temperature 110. Let's start with these 3, guys. The first one, actually, here is very good news. We can go with table A4 or A5. We start with A4 or A5. Both are good. Here, we have A4 or A5. No, A5 is not good because we have 0.03. So it's better to go A4. Both are correct. Here, A4 or A5, both are fine. Let's start the first one. Pick up anyone, A4 for example. At this temperature, what is the corresponding pressure? The P saturation. P saturation at 120 Celsius is equal to what?
198.67.
190. No, I don't think so. 198.67. So your pressure is lower than that. It means you are superheated. So let's plot it again. Plot it here. Let me plot it here, and I'm gonna put it in everything in a big curve. Better to see everything in details. So I'm gonna plot here a big curve. Let's see, when it's like this. Let's say T V diagram. Temperature 120. This is temperature. Say 120 Celsius. At this 120 Celsius, my saturation pressure is 198, almost 200. Almost 200, like something like this. This is P equal 198.67 kilopascal. This is the saturation pressure line. So if I'm moving along this line, I'm starting to see vapor. Everything is vapor. Now, my pressure is lower. My pressure is lower, so I'm 150, something like this. So what is this, guys? What is this point? This is 150 kilopascal and 120. When you plot, for example, XY, if I set X equal 5, Y equal 3, what this point? It's 5 and 3. So this is the coordinates of X equal 5, Y equal 3. You locate the X value, the Y value to get this point. Here, I put the pressure value. This is a constant pressure line, which is 150. I put the 120 Celsius. I got this point. If your pressure lower than saturation pressure, you're a superheated vapor. If your pressure larger than, like let's say here, the saturation pressure, you are compressed liquid. If your pressure is exactly saturation pressure, you are saturated mixture, either complete liquid, complete vapor, or in between. Easy, guys, or not? Is it good? Clear?
Yes.
Clear. So since your pressure lower than P saturation, yeah, I have lower pressure. Water can easily escape, but if I have larger pressure, I cannot escape the water. So here, this is called superheated vapor. If you want to get exactly everything about this point, please go to table A6. Go to table A6, please. If you go down, you skip A4 and A5 and go to table A6. Can you go to table A6? So you'll see it's a bunch of columns. We have pressure 0.001 megapascal, 0.05 megapascal, 0.1 megapascal, 0.2. Let's say you are 0.2 megapascal now. That's, can you see it, guys, or not? Table A6, page number 908. Page number 908. I'm gonna share it again for a minute. Let's share it. So if you see now table A6, I think you can see it now. What happened here, guys, in this table? This is table A6. This is superheated water. At your pressure, if your pressure is 0.0 megapascal, about 10 kilopascal. If it's 0.05, 50 kilopascal. If it's 0.1 megapascal, 100 kilopascal. If it's 0.2 megapascal, let's say we are 0.2 now, or 0.1, this one. This guy, we are 0.1 now. Let's say 100 kilopascal, this guy. At temperature of 120, something between this guy and this guy. Let's say 100 now for simplicity. You can go at your pressure. You can find everything. You can the first column is V, a specific volume, internal energy, specific enthalpy, a specific entropy. So you can find that, let's say your temperature is 200, this grow. So you can get a specific volume, a specific internal energy, a specific enthalpy, a specific entropy. Can you see, guys, this row? 150, 200, this row. Say yes or no?
Yes.
Yes.
Okay, great.
Yeah.
Let's go back to lecture. If you want the more data, if I ask you for here, for example, find the V. There is no VF. This is now vapor. We have V, we have U, we have H, we have information. There is no more VF, VG. VF, VG here. This is VF, this is VG. Oh, here. VF and VG. Forget about them now. Now, go please to problem B, 65, 25.03. At this temperature, you can go to table A4 or A5. Let's take break for now, 10-minute break, and we can come back at exactly 11. Okay? So everyone can go now, take rest for 10 minutes. Guys, if you have any question now, I can answer it now. Like this 10-minute break, you can ask any question.
Will you be posting the homework today?
Today, I'm gonna post the new homework for you, homework 1. So it's due to next week, I think Friday or I don't remember, Friday or Monday. But anyway, you have already the page 4 and 5 in the syllabus. It has all the deadlines. But today I'm gonna post homework 1. And today's problems exactly, mostly will be homework 1. From temperature and pressure, you can how you can see what is this, can fill the table, find the rest of the information. We need to go now with quality, then we'll go with some problem, and that's it. We're almost done with the lecture. We have just quality and more problems to solve. So how about the problems about this? Do you have something unclear? Any for guys? 10 seconds. You have any question? Problem B. We did solve problem 1. We said because the pressure is lower than saturation pressure, it means it's easy to escape. That's why it's superheated vapor. Problem B. Problem B was temperature given 65 Celsius, pressure 25.03 kilopascal. You can go to table A4 or A5, but it's easier for A4. Please go to table A4 and see what the pressure is. Again, see the pressure saturation. If this pressure larger, your compressed liquid. Lower, your superheated vapor. The same, your mixture. So tell me, guys, what is the P saturation here from table A4?
It is 25.043.
Okay, this is 430. So what is this, guys?
It's the same.
The same. It means we are what? We are what? What is this lesion? We're what? Saturated mixture. One word. Since P is equal P saturation, it means we are saturated mixture. Of course, it means, let's say this is the temperature. Here, 65. And the pressure, this pressure exactly 25.043. It means what? I'm here between this point and this point. So what is this guideline? What is this region? What is the region, guys?
The saturated mixture.
Saturated mixture. It means you cannot give me the volume. I don't know where. Maybe here, maybe here, maybe here, maybe here, maybe here, maybe here, maybe here. I don't know. But it's in along this line, of course. It's saturated mixture. Some vapor and some liquid. At 200 kilopascal and temperature 110. It's as you wish. You can go, for example, table A5 with 200 kilopascal. Problem C, go with 200 kilopascal. Find for me saturated temperature at 200 kilopascal is equal to what?
120.21.
100.
20.21.
You did it before. So at this temperature, guys, at this temperature, your temperature is lower. If temperature is higher, you can make it vapor. If temperature is the same, you are mixture. So if the temperature is lower, it means you are what? You are what? Compressed liquid. In order to find the data for compressed liquid, you can go to table A7. Would you please go back to table A7? Open the steam table. I'm going to share it with you guys. This table is called compressed liquid water. This means I have data for this region. This region, I have data for the compressed liquid region. So I have data for this region. This is table A7. This line and this line, A4 and A5. Saturated liquid, saturated vapor. VF and VG. UF and UG. HF and HG. I have data for this region. It's called A6. Let's go back to A7. You have pressure of 200 kilopascal. So first start with what? Pressure. This pressure here. Can you see the pressure? Can you see pressure, guys?
Yes.
But here pressure is too much, like 5 megapascal, 10 megapascal. So it's a little bit large. So if you have the pressure and you have the temperature, for example, here, you can go and get VF, UF, for example, this line. At this pressure, you can. The good news is here, as you can see, for example, VF can look at VF. It's 0.001. V. There is no VF. I'm sorry. V is 0.001. 0.001. Then you can say 0.1, 0.2, 0.3. It means 1%, 2%, 3%. Different than 1 liter of water for every kilogram. 0.001. This number, you will see it a lot. Can you see this number? 0.001?
Yes.
It's everywhere. Every V is 0.001. Even the UF and UG and U and H, so small compared to the vapor. So this energy is so small. The energy in a vapor is like 1,000, 2,000, 5,000. But here is 200, 300. Can you see these numbers? And even entropy. We're going to talk about it. Enthalpy. So all these data are so small because it's just liquid, compressed liquid. Okay? So table, this line, A4, temperature input. This lines, A5, pressure input. A6, A7, 3 regions, 2 lines, 1 point. Okay, guys? Okay. We can do something here. Now, we can do more problems. If I give you pressure, volume, you can see where I am. Okay? Now, we have a problem here, guys. We can get everything for vapor, we can get everything for liquid, but how about mixture? Like this problem. Why I have 2 intensive property? I cannot get the volume. I cannot get the volume. H, I can get here everything here. I can get UV, H, anything. U, anything I can get here. Specific volume, enthalpy, internal energy. But I cannot get here anything. I cannot get anything. You know why, guys? Does anyone know why? The answer is the state postulate, which says if you want the information about compressible fluid, this is compressible fluid, you need to give me 2 independent intensive properties, correct? Do you remember this? You need 2 independent. Independent means they are not related, but at long saturation line, the pressure and temperature related. If I give you temperature here, you know the pressure. This is related along this line. That means they are not independent. They are dependent on each other. But if I give you, for example, here, TMV, you can get everything. You can know exactly where the volume here and the temperature here, for example. You can know exactly where this point. You can get everything, this point. But you cannot get from TMP because TMP are dependent. So that says, you know, if you want everything about data, for example, when I plot this, I said this is the constant pressure line. This is constant pressure line. This is the point. Yes, correct. Bless you. This is like what? So this is the temperature equal constant, and this is pressure equal constant. This is the point I want. Yes, that's correct, because in superheated vapor, they are independent. Temperature and pressure. That's why I can get this one. That's why I can get this one, compressed liquid. But I cannot get it here. Along, if the temperature and the pressure here. So there is a solution. Yes, there is a solution, which is I need 2 independent intensive properties. That's why we define something so important. So from saturated mixture, will be calculated from table A4 and A5. Yes, from A4 and A5. But with something so important, it's called quality. Quality. Something is so important, it's called quality. It's called quality. What is quality? X. Simple new variable is called X. Non-dimensional. It's called X. Quality. What is quality? I give you some water, liquid, and vapor. Here, this is the water. This is the vapor. Pure H2O, pure substance. Some liquid phase, some vapor phase. I'm gonna use everything here. Subscript what? F. Any subscript in what? G. For example, the mass here is mg. The volume is Vg. A specific volume, Vg. So mg, Vg, specific volume Vg. How about here? mf, volume Vf, and specific volume Vg, Vf. Is it clear, guys? Some liquid and some vapor. Okay? Any problem? X is always the mass of the paper over total mass. So M total, this is system. M total is M F plus Mg. How much liquid plus how much vapor. This is total mass. So it's this M vapor over M total. M vapor over M total. Always quality, how much vapor to the total mass. So let's replot the T V diagram. But now we can add new variables. So we have now variables are P, T, rho, or V, U, H. Now we're going to add X. This is the variables we have. In chapter 7, we're going to add new one. It's called S. So we have pressure P, temperature T, density rho, internal energy or specific internal energy U, H enthalpy or specific enthalpy, X quality. New variable is called quality. Can you see it, guys? There? This quality. This is a very important new variable. We're going to see what's going on here now. What is quality is? Quality only existed in saturated mixture. So if you have the TV diagram like this, let's say TV diagram or PV diagram, anything like this. And this is the constant pressure line. Let's say P equal 1 atmosphere, 100 kilopascal, whatever. Along this line is a constant pressure line. Guys, can you hear me?
Yes.
Okay, along this line, constant pressure line. If I give you any point here, you cannot know from pressure and temperature, you cannot. But if the volume and temperature, you can know. Where is it? Like this is the volume, this is called isochoric, and this is called isothermal. Oh, the point is here. This point has new variable is called X. Has variable is called X quality. Here, along this line, X equal, can somebody tell me how much vapor here along this line? Along this line, how much vapor? How much vapor, guys, here? How much gas? How much vapor? This is called saturated liquid. So vapor is what? 0. So X equal, forever along this line, X equals 0. Only VF. You have UF, HF. There is no gas at all. So Mg, if I am along this line, there is no vapor at all. 0 vapor, 0 vapor. X equal 0. How about this line? This a very red line. That's a good color for it. How much vapor we have here?
1 or 100%.
100%. So X equal. So the whole mass, if I have this system exactly saturated vapor, so I have 100% mass over 100% mass. It means X equal 1. How about here, guys? X here is what? And X here is what? There is no X. X only between these two lines. So X, something between 0 and 1. From saturated liquid line, the blue line, to the saturated vapor line, which is the red line. It's impossible to see it outside. So far, so good. So X, 0.1, 0.2, 1, 0, 0.5. It's a mass ratio. How much vapor mass to the total mass? So mg over m total is X. Whenever you see mg over m total is X. mg over m total is X. So if you divide, for example, here, m total here, divide m total here, m total, m total, m total. It will be 1 equal mf over m total plus, what is this, guys? mg over m total. mg over m total is what? Is what? Is X. So mg over m total is X. mf over m total is 1 minus X. Again, total mass is how much vapor, how much liquid, plus how much vapor. Divide by m total here. So m total equal mf plus mg. Divide by m total. This is 1 equal mf over m total plus X, or mf over m total equal 1 minus X. That's very, very logical. Of course, if you have X vapor, you have 1 minus X liquid. If you have X vapor, you have 1 minus X liquid. This is kind of complementary. This is X, this is 1 minus X. The total is 1, which is m total over m total. Make sense? So whenever you see this guy, how much mass vapor over total mass is X. How much liquid over total mass is 1 minus X. Okay? Now, let's do something very simple in math. We know that V total equal total volume F plus total volume G. So if this point here, we have some volume gas and some volume vapor, liquid. Liquid put it here, and gas put it there. Total volume. The total volume is actually the total mass multiplied by specific volume, correct? I want this. That's why I bring this two terms. The product of mass time specific volume give you total volume. This is total volume of the liquid. So mass of the liquid times specific volume of the liquid. This is two terms, mg times vg. As you said before, if you want to go back from intensive property to extensive, you multiply by mass. If you want to go to intensive, divide by mass. So if you divide by mass, this one, total volume here. Let's say 1 meter cube. Some of this volume is vapor. Some of this volume is liquid. The volume, the volume, absolute volume, is mass times specific volume. Mass times specific volume. Mass. Any F means liquid portion. Any subscript F, liquid portion. Any subscript G, gas or vapor portion. The red line. The part of the vapor. The T means total. Divide this by M by V by M total. Divide by M total. Divide by M total. Divide by M total. So this is V. MF over M total. MF over M total is what? 1 minus X. VF plus MG over M total. MG over M total is what? Is X VG. Or take X common factor, V total or V is VF plus X VG minus VF, or V total is VF plus X VFG. This guy, we call it VFG, the bigger minus smaller. This is, for example, 2 meter cube per kilogram. This is 0.001. So this minus, it's approximately VG. So we used to use VG minus VF, VFG. If it's UG, internal energy, minus UF, it's UFG. If it's HG minus HF, specific enthalpy, HFG. Now, this equation is one of the most important equations in your class. Now, we can write this, all the properties now, all the properties. V is equal, the V, which is total or mean V, it's VF plus X VFG. This, guys, is VG minus VF. The bigger minus smaller. U is UF plus X UFG. H equal HF. We're going to take a lot of examples, don't worry. HFG. If you go back to table, for example, table A4, you will find extra columns. This column, for example, maybe this column also of some tables. Go to table, please. Let's go back to table A4, for example. Table A4. Or A5, doesn't matter. If you go back to table A4, let me share with you. So if you look at this internal energy, for example, you will see something called VUF. Can you see? UG. This F means liquid, saturated liquid. G means the vapor part, saturated vapor or evaporation part. This is, oh, sorry, saturated vapor is VG, UG here, sorry, the last one. Then this is the difference. UFG, it means this guy minus this guy. This guy minus this guy. This guy minus this guy. Give you in the middle. Typically, the G part is too big. You see 2000, 2300, something, 2400, 2475. This is 313, 313. This is the difference. It's very close to this. So this guy is U, the bigger, sorry, the U big, it's UG minus U small. Always the bigger minus smaller. Bigger is for vapor, smaller for paper, liquid. Always. If you go to also enthalpy, the same thing for enthalpy. Can you see enthalpy, guys? Here, enthalpy, can you see it?
Yes, we see it.
We have HF, we have HG. The difference is HFG in between. Can you see it? So if you get, for example, this guy, 2600 minus 230, exactly in between, like this, 200, 2369, this one. Why we put these guys? To make it simple for you. Many times you need this guy. So instead of getting UG minus U, instead of getting HG minus HF, we put it for you as a column, as a data. Just use it. It's faster for you, correct? Faster or not? So if you want UFG, it's UG minus UF. This data given, and also this data. It's easier to use this guy instead of these two guys. It's easier to use this guy the middle column between HG and HF. HF in the left, HG in the right. HF in the left, HG in the right. It's clear, guys? Is it clear?
Yes, makes sense.
This is so simple. This is equation linear. This is linear equation. Either this or any of these. Look at this. If x equals 0, this line x equals 0, correct? If you put x equals 0, this is gone. This term is gone, completely gone. It means v equal vf, correct? Yes, along this line, v equal vf, u equal uf, h equal hf. Yes, this is 0, correct? This line, x equal 1. This is the hot line. 800 something. This is x equal 1. X equal 1 is saturated vapor line, completely vapor. There is no liquid. It's impossible to see any droplets of liquid here. X equal 1. Put x equal 1 here. It means this guy is 1. It means this guy will cancel this guy. So the remainder is what? Is what? Remainder is what? Say it.
VG.
Which is complete vapor. It's the same here. This is VG minus VF. If x equal 1, this cancel this, remainder VG. If x equal 1, this cancel this. In between, it's linear. In between, it is how much vapor to how much liquid. If it's 0.5, 50% of this plus this. So from 0 to 1, saturated liquid, saturated vapor. VF to VG, UF to UG, HF to HG. Okay, guys, make sense? Everything makes sense or no?
Yeah, it makes sense.
So I'll give you an example. Let's take an example. This is a new voice. I like that. I like to hear new voices. So these two guys talking a lot. The girl and the boy, I don't remember the name, so don't talk again. Let other people engage it. 101 megapascal, 190 Celsius. Please, what is V here? What is V? What is this type? What is this first? It starts with table either A5 pressure input or A4 temperature input, as you wish, A5 or A4. If you go to A4, you will find this pressure is much lower than, this is 1000 Pascal. This is lower than the saturated pressure. It means you are superheated vapor. You can get V. So please here, help me get V. Somebody tell me what is V is. It means first step, table, let's say A4. At this temperature, we can get P saturation at 190 Celsius. Please, what is this pressure is? What's the P saturation at 190 Celsius? What is value? From table A4. Somebody else different than?
It's 1255.2.
1255.2. It means 1255, correct? It means 1.25 megapascal. It's much larger than this. It means you are superheated. Like this is your pressure. So you are here. You are where? Why you are here? Because your temperature and your pressure, constant pressure line is lower than this value. So this pressure, the saturation value is here. This is saturation value. So you are superheated. You are superheated. Your pressure is lower. So the water can escape easily. So you have now, you need to go to where? Table A what? What is superheated? What's table, guys? A what? Superheated? A7. So please go to table A7. At this pressure, and this temperature, you can find V. Give me V, please. Meter cube per kilogram. Go to table A7, please. At pressure 1 megapascal, you will see columns, pressures. At row of 190 Celsius, you can find this. Okay. Can somebody find the V, please, for me? Guys, are you still alive? I mean, online? Hello? Guys, can you hear me?
Yes.
What is the volume? Specific volume. Table A7, please. Go to 1 megapascal and 990 Celsius to find the specific volume, because we are sure now it's superheated. And by the way, let's say you did a mistake. You are wrong. You did a mistake. You find it superheated, which is not. If you go to table A7, you will not find it. You will not find it. So don't worry. Even if you did a mistake, it's okay, because you will not find it. But if you are correct, you will find this point in this table. So what happened? In table A7, you will find this. You have 179.89.88. Guys, can you find it or no? Guys, can you find it? Please answer me.
Can you show us how on the chart?
Okay, I will do it now. But look at this. This problem is so hard. Why? This is very important problem. This is in every exam, in every homework, you're going to say it. It's called interpolation. If you go to 1 megapascal, you will find only the 200 Celsius. Then temperature after that, 200, like 50, 300. And you will find the V in front of that is 0.02060 meter cube per kilogram, correct? This is table A, table A7, correct or not? Everyone, if with table A7 at 1 megapascal, you find the first temperature 200 Celsius.
A7 or A6?
4, 5, oh, 6. I'm sorry, you're right. 6. The superheated is 6. You're right. Oh, I missed it. 4, 5, 6. This is 6. I'm sorry. A6. At 1 megapascal, 200 Celsius superheated vapor, you find the volume is 0.20602. Make sense? Correct?
Yes.
Any one of you, if you open it, I can show to you it's 0.20602 meter cube per kilogram, the volume at this temperature. If you go back to table, like for example, A4, table A4, at the same pressure, you will find the saturation temperature is what? Almost 180. Correct? Go to back, please, table A4 at 1000 kilopascal or 1 megapascal, you will find the same pressure. The volume is what? 0.1943. If you go, please, to table A4 at this almost 180 degrees, 1 megapascal. Actually, A5 or A4, it's A5 better. If you want to pressure, A5. It's the same, almost 180. Either A5 with this pressure or A4 with this temperature. Did you find it, guys? Somebody say noise or no? Did you find it? At table A5, 1 megapascal, you will find 0.1943. Did you find it? No one find it? I can show it to you if you want.
Yes, please.
Yeah, if you go to table, let me share with you. So here, this is table A4, as you can see, or A5. Let's go to A5 easier. So A5 here, this is 1 from 1 kilopascal to 1000. 1000 is go down here. This is 1000 kilopascal. The V is there's a last V is here, 0.1943. This is called the volume if this is exactly vapor. So if you have this, this is almost 179.88. We have here 200. So you have here, I'm gonna stop sharing. You have here, guys, this point from table A5. This point from table A6, correct? This point and this point. You want something in between, 190 degrees. 190 degrees. So you want 190 degree. What is the volume here? This is called interpolation. Interpolation. So we have kind of triangles here. It's always like this. You have 3 values, 2 values, we need the third one. So simple. It's so simple. Look at this. Look at my pen. This minus this over this minus this equal this minus this over this minus this. It's the slope is the same. This minus this, 190 minus this, over this minus this equal this minus this over this minus this. So if you have a line, you have here x1, y1. And you have here x2, y2. And you want something in between. It's called interpolation. Let's say x and y. This is called similarity for the same slope. This over this equal this over that. The slope is the same. You can use this over this equal this over this. You can use this over this equal this over this. Any two correspond to each other over any two. Follow my pencil. Follow my pencil. This minus this over this minus this. Everything I know. This I know. Yeah, I know. This equal this minus this over this minus this. Let's write it down. I'm gonna write it down for you. Yeah, let's start with V. Let's start with the other side. V minus 0.1943 over 0.20602 minus 0.1943 equals. I said this minus this over this minus this. I need to give this the same sequence. This minus this, 190 minus 179.88 over this minus this, the same sequence. The only unknown here is V. Get V. Which is, I think, was 1.01. It's about 0.02. Can you see it, guys? Sorry, 0.2, 0.2. 0.2, I think 0.2, around 0.2. So what happened here, guys? Focus with this. You will have, this is a very hard problem because you use 2 tables. Usually it's like this. Usually it's like this. You have one table, like for example, 100 Celsius and 150 Celsius. And you have V here, let's say 0.0, let's say 1.357, and this is 1.546. And you want here 120. This is in one table. Usually it's one table like this. You want 120. This is you don't know. So this minus this over this minus this equal this minus this over this minus this. You got it? Is it hard, guys? It's called similarity. Same slope. Interpolation.
Can you repeat that one more time?
Okay, sure. That's actually so simple. Open the table at any, like table A4. A4. Let's say table A4 or maybe A6. Table A6. At 1 megapascal, for example. Please, everybody, open table A4, A6 at 1 megapascal. I'm going to share it with you. Table A6. I can repeat it many times, no problem. No problem at all. Table A6 here. Here, this one. Can you see this, guys? This is table A6 at 1 megapascal. Can you see it?
Yes.
Great. Let's say you take 300 and this volume. 350 and this volume. Give me the data. Let's see temperature and volume. 300 and 350, or maybe 350, yeah. Yeah, guys, give me the volume here. What is volume here? What is volume here? What is the volume? 25799. Here, 0.25799. Correct? Table A6. And the second one is 0.2825. 0.2825. I'm gonna stop sharing now and look at the board. Okay?
Okay.
So we got these values. These 4 values. Can you see it? This,
Yes.
this. Okay? So we got 2 temperatures and 2 volumes. These guys. From table A6. Correct?
Correct.
Okay, what happened here? Let's say I don't want this temperature, this temperature. I want something in between. Let's say 312, like 320, like something like in between. 320. Your problem has 320 and 1 megapascal. So you don't know what your volume is. Your specific volume is. We're gonna do interpolation. Look at my pencil. What you want? This minus this over this minus this equal this minus this over this minus this. You need to have the same sequence. So V minus 0.25794 divided by 0.2825 minus this equal this minus this over this minus this. So what did I here? I said V minus V over V minus V. V minus V over V minus V equal this minus this over this minus this. So I'm using the same sequence. So this minus this divided by this minus this equal this minus this. The same slope. Opposite over adjacent, opposite over adjacent. Or even opposite over adjacent equal opposite over adjacent. This angle is the same. The slope is the same. Tan theta is the same. Similarity to similar triangles. This triangle is similar with this triangle. Interpolation. All of them the same words, the same thing. So all you need to do is like something like this. You can say V minus 0.25799 divided by 0.2825 minus 0.25799 equals what? Temperature 320 minus 300. This minus this over 350 minus 320 and so on. You can get the only unknown is V. Correct? Clear, guys?
Yeah.
So if you have saturated mixture, if you have any of these problems, for example, here for superheated vapor and even saturated mixture, you can do some interpolation. Sometimes the data explicitly not given, like this row. you have this, but I don't want this temperature or neither this. Yeah, I have 1 megapascal, for example, but I don't have this or this. I want what? 320. So I need to do interpolation. So we have a lot of problems, but unfortunately, yeah, we can have 4 minutes. We can do one problem, just one problem. The mixture. Let's do one mixture. Something is so simple. One problem. This problem, guys. Look, this pressure, 10 megapascal, volume is 0.003. Please, 10 megapascal. We started from what? 10 megapascal, and volume is 0.003. Hey guys, 10 megapascal. Let's start with table what? A5. Look at VG and VF. You will find this volume in between. This volume is in between. VF and VG. Please go ahead, table A5 at 10 megapascal. Table A5. You will find this volume between this and this. This is 0.001 something. This is, I don't know, maybe 0.2 something. So then this V is in between. It means we are in saturated mixture. That's easy, that's good. So X equal V minus VF over VFG, which is VG minus VF. So you have this, guys, at this pressure from table A5. You can get X. How much? Mass of the vapor. X is how much mass of the vapor. It's M vapor over M total. How much mass of the vapor? If I want here, for example, U. If I want H. So if I want U, for example, U is what? Is UF, we have it. Plus X, UFG, we have it. Now we have X. X, get it from here. So because he gave you V, he gave you a V, you can get X. Go ahead, put V here, minus VF over VG minus VF, you can get X. Like 0.1, 0.3, 0.5, 0.9, 0.01. How much vapor over total mass? After you get X, you can get any other property in this mixture. So you are here now. Something here between the liquid and the vapor. You are here. You have X. You have quality. Correct?
0.14.
Correct, guys?
It's not between A.
Somebody is putting a mic and talking to us or yourself? Huh? Hey guys, if you go to table A5 at 10 megapascal, which is about 10,000 here, I'm gonna share it again for the last minute. Here, I'm gonna share it. This is table A5. If you go table 5 here, this is table A5. If you go down here at 10 megapascal, you'll find this volume between this value and this value. It's 0.018 and 0.0014. This is 0.0014. This is 0.018. Between, this volume is in between. It means you are a saturated mixture here between VF and VG. You can get X quality. How much vapor to the total mass? This is huge pressure. 100 atmosphere. This is 100 atmosphere almost. Okay. Now we're gonna stop the lecture. It's 11:50. Please go ahead, try to solve the problems given in the lecture. We have about, I don't know. Oh yeah, we have 23, 24, 26, 28, 50, 41, 59, an additional problem. We're gonna solve 3 problems of them in the next lecture and continue. The homework will be posted. I'm gonna post 8 books. If you are interested in one of them, let me know. This Wednesday, you can come and pick up any one of them. But send you an email before you come. Wednesday, before 10 a.m., you can come and take a book. One of these books. It's not a reference book, but a similar one. Okay, guys. Please send me an email anytime. Email anytime if you're interested in any question. If you have any questions, send me an email. If you have any questions, send me an email anytime, okay? Okay, guys?
Okay, thank you.
Okay.
Thank you, Professor. Bye.
Thank you. I'm sorry for this noises, but anyway, have a good summer, guys.
You too.
Yeah.